This question is a good one. It's whatever professor designed this one. I really like it. It shows what we're interested in doing in this problem. Let me actually move you to the dynamic version. Here we go. So look at see I can grab see I'm grabbing this thing at the bottom down here. I'm moving it. Maybe I better be more clear. Let me go back here. So I'm grabbing this right here. I'm grabbing this and I'm moving it right and left, and it connects with the point above. So we're getting 2 points on a graph. This is the graph of y or f of x equals x squared. So this is what it is the graph of y equals x squared, this U shape. Okay. And we're grabbing 2 points on the graph. This point, and now this point is at x equals 1, which is also at a height of 1. So this is the point 1, 1. Okay. And then the other point varies depending on how I move the slider. The other point. And what we want to do is we want to calculate the slope between those 2 points, slope of a secant line. Slope of the line, it's called a secant line between the 2 points. And so, this is going to be up here, this is going to be x1, y1, and this is x2, y2. And you know the slope, how we calculate slope. And so, but the trick is what we really want to do is we would really like to know the slope at just that 1 point right there. Could we do that? Can we get the slope where it barely, I did that wrong. Let me try this again. Where it barely nicks just 1 point? Sort of like that. See how that kind of looks like it just hits 1 point? That's called a tangent line. So we really want the slope at only 1 point. That's the tangent line. So a secant line is a line that hits 2 points. But if you hit a curve and just barely nick it at just 1 point, that's called a tangent line. And that's what we really want, is we want the slope right there, because that's the real slope. Say you're a person walking on this curve, and you're going up here, and you're right here for a second. And when you're right here at the point 1, 1, you want to know, what is my steepness? What if you're riding a roller coaster? Let's put a little roller coaster on here. What if you're designing, or you're engineer designing a roller coaster? And as you go here, it gets steeper and steeper. And you want to know, what is the steepness of the roller coaster right at this 1 point, right there. That steepness is a slope, and it's a slope at only 1 point, not two. That's called the tangent line, the line that hits just that 1 point. That tells you the steepness of the curve right at that point. Well, how do you calculate the steepness of a curve at only 1 point? We know how to do 2 points, right? We can calculate the slope in the slope formula. Slope with 2 points, is y2 minus y1 over x2 minus x1. You need 2 points. That's a secant line, right? But we'd really like to know, in real life, engineers and everybody else who uses this math, all the science that uses this math, they want to know the slope right at this 1 point, not 2 points. I don't want to know the slope from there to there. I mean, that might be useful at times, but also, really more importantly, I'd like to know the slope right at that 1 point. How do you find the slope at 1 point? Well, first off, it's called the slope of the tangent line. It hits only 1 point, not two. And it's a good deep question, which is what this chapter is all about, is how do you do that? Well, let me show you the idea. Excuse me. The idea is shown right here by moving that second point back till it's right on the first point. Do you see that? There it is. That's the tangent line. So I moved it back. See, here it is moving for, here's the second point. I move it back, boom, till it's right on it. That's the tangent line. See how that's nicking the curve at just one point? But of course, if you only got 1 point, how do we calculate the slope? Well, we're going to do a fancy limit thing. That's why we spent all of chapter 2 studying limits, because you need to take the limit as that second point comes back on the first point. And that's what we'll be doing. But first off, let's get the big idea. That's what we want, that second point to come back and land, get as infinitesimally close as it can to the first point. Now, if you get it, see what you want to do is get it really close. If you go down to below, it's showing you the here. Let me do. Yeah, I should be showing that as I'm moving. See, as I'm moving this, it's recal. See that triangle down below? How it's recalculating the numbers as I move it. It's showing us the rise and the run between those 2 points. But if I move it all the way back till it's right on the first point, it's going to go warning. The points should not be the same. When the 2 points occupy the same location, there can no longer be a rise or a run. Do you see what I'm talking about? See that little note that suddenly appeared below the warning there? It's saying you can't have 1 point. Can't have 1 point. You gotta move out and have a second point. Then you have a little triangle which shows our rise and our run. Right? Let's go back to the picture. Right? We're gonna have the 2 points that go from here. Whoops. Try to get this straight here. From here to here. And get a little rise and run between the 2 points. This is the rise, right? And this is the run. That's what we're doing when we do y2 minus y1. That's the rise. That's the difference in heights. This y value, that y value, y2, y1. This is the rise, which is also right there. And then the bottom is the run. It's how far, between this x value, this is x1 and this is x2, right? That's called the run. And we put it right there in the bottom of this triangle here. So anyway, the rise and the run is shown for us here and here. But we need to move the points really close, because the closer the points get, the closer it is to the actual tangent line, because that's what we really want. We'd really like to find the slope of the tangent line. So if I move this back, boom, right there, that's what I really want. I want the slope at just 1 point, but you can't calculate the slope at just 1 point, at least not unless you use a limit, which is what we're about to do in this chapter. But let's, instead of using a limit, let's just put them really close together. And I'm just going to use those two numbers. So I'm going to go to Desmos. I'm going to use, what is it, 1356 and oh 06. See those numbers down there? 1356 and oh 06. So let me use those numbers. In fact, let me bring this back and I'll put it right here for us. I'll get rid of this one and I'll put in this new one. And let me get rid of my scribbles here. And I'll put in that new one I just did. There it is. All right. There we go. Okay. I did this dynamically for you. So there we go. So this is the rise and this is the run. And so the slopes, see, these are the 2 points really close together. Slope is going to be the rise, 0.1356 over the run, 0.06. So 1356 over 6. Then let's go to Desmos, right? Do I have Desmos open? Yeah, I do have Desmos open. So you can get access Desmos during the exam, homework, everything is right on the website. What was it, 1356? Yeah, 0.1356 over 0.06, I think. Isn't that it? I'm getting 2.26. 1356 over oh 06, 2.26. 1356 over oh 06, 2.26. So type that in. that'll be very close to the actual thing. Here, watch me do it dynamically. 2.26, 2.26. If I come down here and I say, okay, I think it's 2.26. It's actually 2.2. You can see the answer there. I'll go to, if I say 2.26 and submit it, it says, that's close enough. The exact shape is really 2.2, close enough, right? Because we got those dots really, really close. Now, if you type in an answer that's not close enough, then you got to move the dots closer together. So that's the point of this example, is showing us that what we really want is we really want the slope at just one point. But our slope formula is all about 2 points. So we have to move the second point really, 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 really close. And then we can estimate the slope at just one point, which is really what they want in real life engineering and things. You want to know the slope at one location. Say if you're building a roof or you're building a roller coaster or you're building something in a car, you want to know the slope right at that one point. And so you have to move the second point close to the first. And what we're going to learn is you actually have to take the limit as that point gets infinitely close. Second point gets infinitely close to the first. Then you can calculate the exact slope at only one point. We're just estimating right now. That's the big idea of what's called a derivative, a slope at only one point. And so that's all we have to do on this problem.